Okay, good morning everyone. So today we are going to look at data mining. So yesterday we looked at data, how data is represented, what are the different types of analysis one can perform. And then we also looked at how data is managed in a file system, in a database management. So today we are going to look at the data mining landscape. Now, I should warn you that there is a lot of work that is done in data mining right from the 1960s. So there is no way we are going to cover all of that. So what I'm going to do is to give you highlights of what is data mining, why it is important, what we should be careful about while doing mining, and what are the important things that you need to take into account. So that's what we are going to do. So data mining is also known as knowledge discovery. And yesterday somebody was asking, what is the difference between querying and data mining? Hopefully you will get an answer today. And if you still don't get an answer today, come and talk to me. I will try to explain. So this one, the key in business is to know something that nobody else knows. So then you have a competitive edge, and that is how it got started. So keep that in mind. So here is a motivation for traditional training. How do you find these guys? There are 10 billion records on 10 million customers in the main database. With all this information we have about our customers and all the calls made, this is from a telephone company. Can't you just take the database to figure out which lines have been set up temporarily and exhibited similar calling patterns in the same time periods? The information is in there, I just know it. So this is what is the expectation. So what is the difficulty with this? The difficulty is finding similar problems just described is very hard. So similar is not exact. So similar is something that has to be defined in some way, and it may vary from domain to domain, context to context, and place to place. So find similar problem is very hard. Who should be given incentive? So in a company, there is always this decision making. Who should be given incentive, and then the managers or somebody makes decision based upon various factors that are associated with that. Now it's very difficult to quantify them in a query. How can we group usage patterns into similar groups? How can we say this pattern is similar to this pattern, but not the same? And there are multiple patterns that are different from each other. Should we approve the purchase by this credit card by this user? This is one of the problems American Express card tackled in the early 70s, because that is the only card that did at that time real-time approval of credit without having to check anything. And they had a expert system to do that, which is similar to data mining. So why? Massive amounts of data, more and more online data stored, web corporate database. Challenge is real-time versus post-mortem. So this is important to understand. Some problems need to be solved in real time, and some problems is not necessarily need to be solved in real time. For example, if you are talking about cyber attacks and other things, you want to be able to do it in real time. If you are monitoring for air quality, water quality, and other things, you want to be doing it in real time. But there are situations where you can do after the fact analysis for understanding what has happened. So if you have, for example, valet footage or footage of some other place, then you can analyze that. So there is a difference between post-mortem analysis, which is also called forensic analysis, and real-time analysis. So no easy way to describe what to look for. This is the key. If there was an easy way to describe, then we could formulate it as a query. There is no easy way to describe because it changes from domain to domain, context to context, and what you're trying to do. This is the real problem. Traditional interactive query-based approaches fail because you can only extract information, but you cannot see what the groups of patterns are. Size of data, different purposes, need for domain knowledge, all of these become relevant. So data mining is part of the knowledge discovery process carried out to extract valid patterns and relationships in very large data sets. So certainly you should understand why and how this is different from query processing or even search. Usually don't know what to look for, like a voyage into the unknown, regarded as knowledge discovery or learning from basic facts and data. And this has roots in AI and statistics. As you know, today there is more and more of AI, machine learning, neural networks, and a lot of statistics that is being used. Uses techniques from machine learning, pattern recognition, statistics, databases, visualization. So I want you to clearly understand that data management, data querying, report generation is different from data mining. In data mining, many times you do not know what you are looking for. You want to figure out what the data contains before you know what to ask for. This is true in association role mining, this is true in clustering, this is also to some extent true in classification. So what to do? A few months before the contract expires, this is with respect to ISP phones I was talking about, if we can predict which customers are likely to quit. So remember we talked about predictive analysis. Here you need to predict which customers are likely to quit, then give incentive to those who are likely to quit. Don't do anything for those who are not likely to quit. So the question is, so because they don't want to give incentive to every user, right? That becomes too expensive, too costly. So they really need to understand who is likely to quit and who is not likely to quit or switch. Then they want to target them. So this is known as target marketing. So most of the target marketing, like some of the mails you get for, we will give you a credit card, apply, you have been selected for this and all. They're all target marketing generated by mining algorithms based upon your characteristics, your income, household income, for example, your spending pattern, your age group, your demographics, whether you are a male or a female, what kind of things you buy. All those things come into picture to determine whether you are a target for pushing a particular credit card on you and making you buy that. So the main problem in data mining is how do I predict this behavior and corporate palm reading. We are very familiar with palm reading and horoscopes, human intuition, and data mining, knowledge discovery in databases, that is known as KDD. There's a whole conference devoted to KDD today, and it has been going on for the last 15 years. So this is the basic problem, I hope. How did the current avatar of data mining come about? It did not happen overnight. Mining has been around for a while. As I said earlier, people have been looking at samples and examples. There was something called example-based reasoning. So there has been a lot of work on. So earlier, humans and earlier work focused on looking at a few representative samples and try to generalize from them. That is what still humans do. But computers cannot do that. Computers don't know how to generalize from small set of samples. That is why we use very large amounts of data when you are doing mining in an automated manner, because larger amount of data is much easier to recognize patterns. So enablers, what are the enablers? Cost of storage. So earlier you could not store a lot. Remember I showed you disks that had 5 megabytes with a fridge-sized disk. Today you can hold that in your pen drive. Reduced cost of processing. Machines have become faster. Perhaps you remember Moore's law. that every 12 months the CPU processing doubles. Ability to store, process, and manage large volumes of data, databases, data warehouses, and internet. New techniques such as association rules I mentioned for market basket analysis, sequence data processing, ontology, stream data processing, information fusion. However, the biggest problem is scalability, understanding or interpreting the result, which is part of visualization, variety of data you have to deal with, filtering very large outputs are new and important issues. So these are the challenges in this domain. So what are the technological advances that gave rise to this? One is increase in processing capabilities. Second is advances in storage technology. And then increase in network capability, reliability, speed, and all those things. This is also one of the things that has contributed to cloud computing, which we will see in the next lecture. So all these together came together to facilitate data mining, application of statistical machine learning algorithms, systems plus architecture. So although this was being done on a small scale, doing it on a large scale was not possible earlier. So these technologies and software developments facilitated that. So this is typically what is considered traditional data mining. You have some data. It may be loan data. Suppose you are working in a bank and you are applying loans. So how do you determine whether an applicant who has applied for a loan is a worthy candidate for approving the loan? So that is something for which you have to predict. So from the data description, you can do a bunch of different things. I have just listed a few things like clustering, classification, association rule mining, anomaly detection, regression, subgraph mining, and then you get the final results, and somebody has to interpret the final results and use that in a particular way. So this is how we were doing traditional data mining, and for each of them we had different algorithms, different packages, different way of looking at the data and then analyzing. So in data mining, a domain expert assists the analyst to determine the best mining. So this is important. If you are giving a loan, you need to understand some of the details of how a bank performs, what kind of loan you should be given, and what kind of return you can expect and all those things. If it is classification, it's a different thing. So for example, for direct marketing, typically classification is used. Interpretation of results is the most difficult and important. So I want to emphasize this because it is not just a question of running a package and outputting the result. Somebody needs to understand the results and sort of see whether it makes sense or not. Not in every case it will make sense. Sometimes the results are counterintuitive. You never thought about this, but when you see that, you think, haha, this is possible, and I can understand how this is possible and do that. So there is that aha moment in exploration and knowledge discovery, which is sort of not present in query. So applications, these are the applications that are customer profiling, which is finding new customers. So if I am selling a product, how do I target who I should approach for buying that particular thing? So that can be done using customer profiling because I have lots of data from the past buyers. So I have plenty of data from the past buyers and now can use all that data to determine who could be the current buyer. So remember today, irrespective of what you do, even if you buy a small thing, immediately you get a survey. Why do they ask for that survey? Exactly for data mining. So they will ask you for your gender, your location, your income level, and your household information and all that. All of them contribute to target marketing. Market basket analysis. So I mentioned this We're not going to this a big thing, Walmart and D-Mart kind of things do that. Amazon being an online thing, it doesn't have to do that, right? Because there is no placement of objects next to each other. You don't walk through the aisles, look for this or look for that. Managing inventory, so that is part of risk analysis. So for insurance companies, use this risk analysis whether to give you an insurance or how much to charge for your insurance if you are a high risk. Insurance, loan, stock, text analysis, library, web, fraud detection, this is very important. Customer relationship, marketing, scientific discovery, forecasting, etc. So all of these applications have been benefited by data mining, earlier data mining techniques. Any questions? So what is data mining? So this is very important. The next two slides, I'm going to ask you some questions, and I want your answers to get an understanding of how you understand data mining. So to understand data mining clearly, one needs to differentiate between two concepts. The first concept is the notion of causality. I'm sure most of you are familiar with the notion of causality. And second, the notion of correlation. So correlation is a mathematical or statistical thing that you are also perhaps familiar with. So it's very important to understand these two and also the differences between these two in order to appreciate and understand data mining. So one is based on semantics. So causality is based upon semantics. Causality means one follows the other. If this happens, then I know this will happen. So that is cause and effect. Whereas that is based upon semantics and intuition. Whereas correlation is not based upon semantics and intuition. It is based upon how data patterns fit together. So you take different sets of data and see what kind of relationship exists between them. So that can be quantified mathematically, whereas causality is much more difficult to quantify. So what is data mining trying to do between these two? So here is your understanding. So what is causality? So we understand this as cause and effect. Heavy rains means flooding. So there is a cause, there is an effect. Flooding will not happen without heavy rains. So there is a cause and effect that we understand. What is correlation? Correlation is different. It's a mutual relationship or connection between two or more things and their strength. So you can see that as temperatures goes up, ice cream sales goes up. So these are two independent things, right? So you can track the increase in temperature, you can track the increase in ice cream sales and see whether there is a correlation. Is that true? So that is correlation. So if you understand this clearly, if not, ask me. I'm going to ask you a couple of questions. So in correlation, you can also have positive and negative correlation. That means this corresponds to, so you can say if it is winter, maybe ice cream sales will go down. That's a negative correlation. But if you go to European countries, actually ice cream sales go up in winter. So that's a different thing. It depends upon the context. Here, people drink hot water in winter. There, people drink cold water in winter. So there are differences. That depends upon the data set, where the data set comes from. So, do the above two mean the same thing? That is the first question. Are these two same or different? Is causality the same as correlation?
No.
This is the litmus test for whether you understand data mining or not. All of you have taken a course in data mining? Yes? No? maybe, forgotten, long time ago. Anybody?
So these two are different, totally different. So these two terms are totally different.
They are different. You're absolutely right. These are different. So we need to understand why. Now, important to understand why. So which of the two we want to identify in mining? So when we do mining, do we want to infer causality or do we want to infer correlation?
Correlation.
Huh?
Correlation.
No. See the underlying thing. What do we want to infer? Do we want to infer causality or do we want to infer correlation?
We need to infer causality.
Huh?
We need to infer the causality.
Which one?
Causality.
Causality. You're right. So we want to infer causality, but that's what we want to infer. Which one does mining actually identify?
Correlation.
Correlation. Why? Why can't we identify causality? But we also know that correlation does not necessarily imply causality. We know that. But causality implies correlation. But correlation may imply causality, may not imply causality. That is the best we can do. This is also the reason why we need domain understanding or domain expert to understand. So the reason, let me see, so why? Why is that? Okay, so this is something I show. I don't know whether it will come up. If I click on it, can you click on that link?
Try clicking on the touch screen.
Can I do that here?
Yeah.
Is there internet here?
Yes.
Ah. So I don't know whether it will advance. Ah, okay. So here are some examples. There is a website called Spurious Correlations. So look at this. I'm not going to show you everything. Look at this. Popularity of the dumb ways to die meme correlates with the number of electronics engineers in Utah. This is a strong correlation, but this is not causality. So this is what you need to understand. Just by looking at correlation, you cannot conclude that dumb ways of dying follows electronic engineers in Utah. Similarly, I won't show many things. So here, okay, so liquefied petroleum gas usage in Spain correlates with assistant professor salaries in the US. So I really want you to understand this, because even though we determine correlation, because we have a mathematical way to determine correlation, we don't have a mathematical way to determine causality. So we determine correlation, but you should not conclude only based on correlation that there is a cause and effect between them. That is where the domain understanding and domain expertise comes into picture. Anybody can look at this and say, this does not make sense. But number-wise, data-wise, it makes a lot of sense. There's a strong correlation, but causality is not there. Okay, so how do I go back to my original slide? Okay, so do you understand now? Causality is a more intuitive semantics concept. correlation is a mathematically defined concept. It's easy to calculate correlation. It's very difficult to calculate causality. So what we do is, most of the mining algorithms do find the correlation, and from then we try to map it into causality. This is very, very, very important to understand what mining is. So I said what mining is. Now what is not data mining? Is there something called data mining, or everything is data mining? Data warehousing is not data mining. Data warehousing, when you ask OLAP queries, it's a query. You formulate the query and you get the answer. Ad hoc OLTP, online transaction processing, is also not data mining, because you formulate a query, whereas in data mining, there is no query formulated. Online OLAP aggregation, summary, data visualization, agents, mediators. So don't confuse buzzwords. There is a lot of buzzwords floating around, and people are confused between what is this versus what is that versus what is that. So don't get search, look up, they're not mining. So here is another brain teaser. So this is purely my opinion. Are there things data mining is not likely to do? If so, what kind of things are they? Today, with AI and ChatGPT and LLMs, we have a tendency to think it will do everything. It can do everything. But I personally think we are still a very long way from some of the things. It can do a lot of things, no question about it, no doubt about it. It's very useful. I use it in many situations. But there are things that are beyond the purview of that. So let us take an example. Data mining cannot substitute for human intuition and generalization capability. Humans are capable of taking very few small examples and generalizing. Computers cannot do it. Machine learning algorithms cannot do it. They require very large amounts of data to figure out things. Have to wait and see where ChatGPT takes us. I don't think DM systems will discover. So I was in a workshop with physicists. All of them were renowned physicists, and I asked them this question: can data mining discover equal to MC squared? And their thinking was, no, it cannot. This is not something that is purely data driven. This is based upon human intuition, human faculty and understanding, and various understanding, which may or may not reflected in and we don't even know what data to look at. Similarly, there is a famous formula in chemistry, PV is equal to RT. Gravity, Newton's laws of motion. Newton did not go and look at 10,000 apples falling every day to determine gravity. It just occurred to me in an instance when he looked at one of them. So it's not the question of looking at very large amount of data and generalizing and concluding. Okay? It may discover new black holes. So here is the difference. You can collect a lot of data. These are being done. Like I told you about the God particle the other day. God particle was there was a conjecture, but there was no proof. There was no experimental result to say that. And that came from the Hadron Collider. Similarly, things like black holes and all, which are again, all of these are proposed and then experimentally verified. Remember I talked about two ways of independently verifying things. And this is also true for equal to MC square. I should tell you this anecdote. I know I may exceed the time, but this is interesting. So Einstein published his paper on equal to MC square, but there was no way to verify it. It was completely theory, and he proved it and showed it. So the problem was, it was not an experiment that you could set up in the laboratory. They had to wait for 2 years for a full solar eclipse to verify his theory. So 2 years after the publication of his journal paper, not him, all other scientists, some of them agreed with his theory, some of them did not agree with theory, went and collected data for a full solar eclipse to determine whether the theory was correct or not, and it turned out to be perfectly correct. So this is the difference. He was able to formulate it even without looking at any data. The data came 2 years later. So people traveled to different places on Earth where that eclipse was visible, collected the data, and then matched it with this formula, and it was correct. So this is the difference between what we can do with computers and what we can do with human ingenuity. The value of pi perhaps can be determined because if you look at a large number of values, diameter and circumference, you can get a generalization. Okay, so much for that. So I hope you understand the underpinnings of what data mining is and why it is different from what was being done till then, and what it produces. It produces a different thing that we don't know many times. So data mining tracks, prediction, descriptive methods, use some variables to predict unknown or future variables. So this is very important. This is, it will come. Descriptive methods, we talked about it, find human interpretable patterns, and this one, types of data. So this is the other thing that you should understand and remember. There are 3 types of data mining. One is supervised. What is supervised? As the name says, driven by known information about data. We call it labeled data. So what is an example? A good example that you can understand is weather, right? For weather, we have a lot of good data. Once the day is over, we know exactly what happened, right? And we have all the parameters, temperature, wind, humidity, sun or cloud or whatever it is. So we have years and years worth of accurate labeled data. This was the variables, this is the outcome. These are the variables, this is the outcome. So the question is, can we use that data to predict future weather? So if I know the weather for the last 1 year, can I predict tomorrow's weather? So that is what is supervised learning. So you use the existing correct data. By the way, we call this ground truth. This labeled data is known as the ground truth. So you use this data to derive a model. And you use that model to data that you don't know. This is also true for target marketing. So if a company sells newspapers or magazines, they have a lot of people who are buying them, right? They have all the demographic information on them. So they know who buy them. Now if a new customer comes, they can match it with that one and see whether he is likely to buy it or not. So in situations where you have labeled data, ground truth information, this is a very effective technique. Classifications essentially is based upon this. Optimize existing solution and markets. So that is one form of them. But there are other things where we don't have this kind of data. Suppose say you are given a bunch of points and you say, I want to cluster them. We don't know them, how they cluster. This is also true for graph mining, we'll see that. This is also true for market basket analysis. We don't have any ground truth. We don't have any information, but still we will be able to derive information. So driven by no known or labeled information about data. That's why it's called unsupervised. This is truly exploration, figuring out something that we do not know. And relevance, finding new patterns that may be counterintuitive, relies on domain knowledge to validate. Finally, there is something called semi-supervised, driven by small amounts of labeled data and large amounts of unlabeled data. So this is also becoming very popular. There is also something called self-supervised, where it tries to create its own labeled data set in the process of doing things. And all of these techniques are used in different places in different ways. So sample DM approaches. So classification is one of them. I will not go into the details of that. There's a whole set of papers, but you know what it is. So this is a supervised approach. Why? You take labeled data and create a decision tree. And you use that decision tree for unseen data. And if the model is correct, your result will be correct. If the model is not correct, it will not be correct. So that's what this is. Clustering. Clustering is typically unsupervised because we don't know. Given a pattern, we don't know how many clusters are there. So we may say, okay, identify 3 clusters, then it will identify 3 clusters. If you say identify 4 clusters, it will identify 4 clusters. Association rules. This is, by this time you should know, nobody is answering, so I'm not asking. Unsupervised. Text classification, typically it is supervised because you have a lot of information that you can use as labeled data. Anomaly detection, supervised or unsupervised? Unsupervised. Graph mining, this can be both supervised or unsupervised. You can give some positive and negative samples and then ask it to do inference, or if you don't have any samples, then it will do other kind of inferences and so on. Neural networks, supervised, unsupervised. If you are into AI, you should know this. Typically, neural networks are supervised. You have to fine tune the weights. And back propagation, for example, in order to make sure that it gives correct results on lots of labeled data so that you can rely on it for unlabeled data. Deep learning, same thing, can be both self-supervised as well. Big data analytics, it can be both descriptive, prescriptive. This is what you will be doing most of the time. If you become a data analyst, if your goal is to become a data analyst or a researcher, you really need to fully understand this. Okay. So a lot of people think data mining are just algorithms. So there are various algorithms, clustering algorithm, classification algorithm, association. But it is not. You need to understand that there is a whole life cycle. You start with the data. It doesn't matter where the data resides. It may be in a database or outside. Then you have to do a lot of selection. As I said earlier, not all pieces of data are needed for all mining purposes. So you have to identify which data is relevant, which is not relevant, and then you have to do some pre-processing. There may be incomplete data, there can be null values, there can be values that are not properly done. So you have to fix those things, and then you go to data mining. And then you have to do analysis. Once you do the analysis, it is not necessary that you get the final result. You may have to rethink and go back and change a few things. So this is an iterative process. Data mining is typically an iterative process, not a single shot process. It is not that you get your answers the first time and the correct answer. So this is important to understand. So there are different kinds of models. Some models are better than others in terms of understandability, in terms of accuracy. They range from easy to understand to how do I interpret results. So here is just a spectrum. Decision trees are easy to understand. They can be cast into if-then-else rules. It is easy to understand by humans. At the other end of the spectrum are neural networks that are very difficult to understand. You know you are getting the correct results, but you don't know why. And it's very difficult to explain what is happening in between, especially if you have multiple layers of neural networks. So that is something that you're, and other things, 10 nearest neighbor rules, and other things for you. Using a model. So you can have a qualitative model, gives the analyst an understanding of the rules. If 35 age is greater than 35 and less than Y, then buy expensive cars. Assume you have made enough money, you are willing to buy cars. But now with all the inflation and uncertainty, you may change that to if age is greater than 25 and 35, then trade your expensive car to an average car. So this can be a different rule. Interaction with the model and visualization is important. Quantitative, it's an automated process. Classification, scoring, so essentially you get a score. You get a probabilistic value or you get a confidence. They'll say this can be the case with this confidence. So higher the confidence, the better it is. The lower the confidence, not so good. So how do you test a model? Suppose say you have generated a model using supervised data. So when you generate a model, you always generate a model using supervised data. And this shows briefly, so here is the data that is used for training. And then this is the new data. So historical training data, from this data you generate a model and then you test that model to make sure that, so you train with some data and you test with some other data. From the labeled data, both from the, because you know the answer here and you know whether this model will be correct or not, that will give you the accuracy of the model. Then you use it on the unseen data. If the accuracy is high, then you are confident that it can be used on the unseen data. But doing this kind of model testing, just using one piece of trained data is not enough. So that's why we have what is known as, K cross validation, 10K cross validation, 5K cross validation. So what you do is you take the labeled data, divided it into K parts, use one part for training, use all other parts except that for testing. Then you train with this part, do the same thing. You train with this. So if you do that, then you can get an average accuracy of the model. So cross-validation is very important to make sure your model produces the kind of accuracy that you are interested in. So application of statistics techniques have been waiting for technology to catch up. The reason I say is that before the automated use of large data, scientists were still doing sampling. Sampling is a very important concept, especially random sampling. It's very important, so you can take a very large data. If you don't have the processing capability, or if you want to look at it manually, you can take a representative random sample and work on it to understand it. So that's what I tell my students to do, even if they are doing very large data. Don't start with a very large data. Take a small sample that you can understand, you can figure out what is going on. Run it with the same algorithm, see what you get. Once you are convinced that it is working correctly on a random representative sample, then you are more confident that the result. So this is part of the sanity check. Remember I mentioned sanity check and validation. So cross-validation is part of the validation, and doing it on a small sample is part of the sanity check. So statistics have been good data mining, the intelligent application of statistical process, emphasis on scalability, handle large data. So the move from sampling to automated things came about because of the processing speed, because of the increase in data, because you wanted to deal with real data rather than small set of data. So classification can be done using neural networks, decision trees, KNN, base classification, support vector machines, clustering, prediction, association rules. There are a lot of algorithms, time series analysis, text filtering. This is what I was trying to indicate the other day. It is not just one algorithm that you can use all the time. It's a toolbox. So the important thing here is how do you choose your tools for the problem at hand. You know, a few years ago, I visited a company in Bangalore, and they said, sir, you know, we have tie-up with an American company and we have lots and lots of data, and they want us to do these things and we are doing it. So I asked them, how are you doing it? He said, sir, you know, we have 25 different algorithms. We just run each algorithm on the same data set and see what it gives. I felt that this was the wrong approach. You just don't exhaustively run all the algorithms on data set, then how will you decide which one is good? So it is not enough to have large amounts of algorithms that you can apply. Anybody can apply. An undergraduate can run the program, feed the data, you get the result. But then what? So people don't think about it. People only think about, hey, my program ran, it gives an output, so it should be correct. If the program runs, that means it is syntactically correct, not semantically correct. It may be giving wrong results. So keep that in mind every time you write a program. Metrics for performance evaluation. Focus on the predictive capability of a model rather than how fast it takes. Efficiency is important, but accuracy to me is more important than efficiency. So what is the accuracy of a model? How do we quantify it? So here are a few examples. Suppose we have a model, we have created a model and a test data set. We have 1000 test data points, and we know because it is labeled data, 550 are actually correct, yes, 450 are no. This we know. Now we run this test data set on the model and get its output. Suppose the model predicts 500 instead of 550 as correct, and 100 instead of 450 as not correct. So what do we understand from this? How can we figure out? something about this model. It is giving some correct answers, some incorrect answers. So how do we figure out? And in order to do that, there is something called a confusion matrix. You might have heard of a confusion matrix. So this is what is typically used. So in order to use that, you have to understand four things. What is a true positive? Data points that are labeled as positive, that are predicted as positive. They are true positive, means they were correct in the label, they were correct in the prediction. True negatives are also important. They were negative in the label and predicted as such in the label. But here we only have 500 out of 550, 100 out of 450. So what happened to the rest? The rest becomes false positives and false negatives. So what is a false positive? Data points labeled as negative that are predicted as positive. So that is a false positive. False negative is data points labeled as positive that are predicted as negative. So if you understand this, what we want is these two. These are errors. So we represent this in a confusion matrix like this. This is the actual label. This is the predicted class. So in this data set where we had 1000 data, 550 were actually yes, 450 were actually no, only 500 were detected as true positive, 100 was detected as true negative, 350 as false positive, 50 as false negative. So these are incorrect. So how do we compute the accuracy of this model? So the formula that is typically used is this one. This is a very simple formula. Take the correct ones, divided by the total. So here, 500 plus 100 divided by 1000.6. So what it means is, this model is accurate only 60% of the times. 40% of the times it does not give correct results. Now we want this accuracy to be, when is this accuracy 1? Under what conditions is this accuracy 1? When this becomes 0 and this becomes 0. If these two are 0, numerator equal to denominator, accuracy is 1. So that's what you want. But these errors, the more the errors, the less the accuracy. Okay? So why is accuracy so good? So here you can see that there is a disparity between, not so good, disparity between higher number of false positives that will pull down the accuracy. Either this or this will pull down the accuracy. FP is high. If FP reduces to 100, then the accuracy becomes 0.85. And if both of them become 0, accuracy becomes 1. So here is another, so this is more or less what we call a balanced data. Why is this balanced? Because the yes and no are more or less in balance, the equal amounts. Slightly different, but equal amounts. In this data, they are imbalanced. There are 2,450 test data. 2,000 are yes, 450 are no. So there is an imbalance between these two. And you do the same thing, and then you compute, the accuracy is 0.244. So you see that, some models that may give better accuracy for balanced data may or may not be able to give good accuracy for imbalanced data. What contributed to low accuracy? mainly the large amount of false negatives and also this. Another imbalanced data, 2100 data, 2000 yes, 100 no. Here is the distribution. Now you can see that these two are relatively low and hence the accuracy is very high. So it depends upon the generated model. Depends on the representativeness of, this is very important. This is the reason why we do 10 cross validation. Because if you just take one set, 1/10 of that, it may not be balanced. When you do this cross validation, you will see that some of them will give high accuracy, some of them will give low accuracy, mainly because of the non-representativeness of the data. Imbalanced data sets are common in medical, security and other fields, so you need to deal with that. Same imbalanced data with a different approach. 2100 data, 2000 is same as before. Suppose I throw away my model and I say yes to all of them and 0 to none of them. If you do that, the accuracy is very high. So this is a problem, right? I'm not even using a model, I'm just, because it's imbalanced, by choosing which ones to say yes and which to say no, I can achieve high accuracy. So this also means that this accuracy equation, this accuracy model may not be very good, may not be correct. It may be good for balanced data, but it may not be very good for imbalanced data. So what is the problem with this approach? A single measure of accuracy does not seem to tell the whole story. So because of that, they have introduced, another thing that you need to take into account is the cost. What is the cost of correct prediction and what is the cost of incorrect prediction? Okay, that's very important. Especially in some fields, you are classifying a patient as having a disease or not having a disease. Cost of classifying a patient who does not have a disease is having a disease is one thing. That's an incorrect prediction. Cost of classifying a person with a disease not having one. The question is, which one is worse? A may be acceptable if there is a simple, inexpensive test to confirm that. On the other hand, B is not acceptable. The cost is too high. Somebody has a disease, but you have said you don't have a disease. That person goes away and dies after a few months. So this is what you have to deal with in real world data. Okay, it's not just playing with numbers. You have to deal with the impact of what these models give you in real world. So, in order to, same for crime, putting someone away for 10, 20 years if there is no crime committed because some model predicted that he was a criminal. Legal matters, student grades, you don't want to give a wrong grade. Stock market, if you make a blunder in stock market, you lose all the money. How can we include cost in addition to accuracy? So there is a cost matrix. So you can associate a cost. You can associate a low cost or a high cost depending upon the semantics. This cost is not fixed. This cost varies from domain to domain and the impact of the error. So here, for example, for this one, there is a very high cost, which is the other one we talked about. And you can now compute cost-based accuracy. So accuracy is 60%, cost is 4900, accuracy is 70%, cost is 8950. Then you have to determine which model is better and why. Is cost more important or is accuracy more important? That may depend upon the domain. So again, these are all ways of looking at what we should do, but somebody has to make decision. The mining system is not going to make this system. This is what I want you to understand. There has to be a human in the loop to make decisions along the way, even if you automate things. It will only output numbers. You have to interpret that and see whether it makes sense. Which classifier would you choose and why? Do you want low accuracy, low cost, high accuracy, high cost? Cost versus accuracy. So I'm going to skip a couple of these like this. You can look at it. I want to get into, so this is important. So there are two additional notions in addition to accuracy, which are called recall and precision. Recall says what proportion of positive values does the model capture. So this is this value over this plus this. So all of them have been predicted. So this was true but has been predicted as no. So this is the recall. So it only was able to recall TP out of TP plus Fn. Precision is this way. What portion of positive values are correct? So TP is correct across TP and FP. This was also is a false positive shown as correct, but it's actually not correct. So precision is this one. So there are two notions of thing. So recall and precision. Again, when you do mining, you not only compute accuracy, you also need to calculate recall and precision. Sometimes, if the recall is very high, no, I just have a few more slides, finish it off.
Third lecture,
Huh?
Is it third lecture or fourth started?
This is the fourth may be a little bit short, so together. There are a few more slides, I'll wrap it up, this module.
No,
Okay, that's,
you can continue it after 2 seconds. So you can just
That's fine.
what level this is?
that's fine.
Because if you continue, then you might have
Yeah.
like,
No, that's okay, we'll break.
okay, let's take a break, okay? Tea is outside this hall. Please join us for a tea. Come
So again, welcome back. So we've been discussing recall and precision. Now these are conditional probabilities. You might remember. This is the conditional probability of S when it is actually yes, yes when it is no, yes, yes, no, no. So they correspond to these things. So recall and precision are quite useful. So the question is, now we have accuracy, now we have recall, now we have precision. We know that we want recall to be high, we want precision to be high. Recall is 1 when this is 0, precision is 1 when this is 0, as usual. But they may not be 0 at the same time, they may be different. So the question is, can we reduce precision and recall to a single number instead of 2 different values? How should we combine them? So is it possible to combine? So there are different ways of combining them. You can use arithmetic mean, you can use geometric mean, you can use harmonic mean. So it turns out that, so this is the same thing. So it turns out that arithmetic mean is not good, geometric mean is also not good for that. So note that recall is 1 for max. When Fn is 0, note precision is 1. What we want is for both to be high. When both are 1, the model is perfect. Arithmetic mean will not work well at the end points 0, 0 and 1, 1 as 0 and 1 correctly. We also want it to be low when 1 is 0. So mean is not appropriate. So mean, if you use the mean, this is what you get, and this is not what we want. So we use the harmonic mean, which gives rise to this guy. So this fits what we want for recall and precision better than the arithmetic mean, because you see this is a curve where it is 0 here, and 1, 1, whereas this one is not 0 here, this has a different value. So arithmetic mean will not give you a good evaluation of recall and precision. So looks for harmony in numbers. So harmonic does this. So that's what we use. So when you do data mining, when you develop new algorithms, when you do all these things, you compute recall and precision. You also compute F1 score, which gives a combined information about your recall and precision. If both recall and precision are 1, your accuracy will be 1. If one of them is low, then it will not give you a very low value. So F1 score is defined as 2 times precision into recall divided by precision plus recall. F1 score for 0, 0 is 0. F1 score for 1, 1 is 1. F1 score for 0, 1 is 0, not 0.5 as in arithmetic mean. F1 score for 1, 0 is 0, not 0.5. So this is the main difference between using arithmetic mean and harmonic mean. So harmonic mean models recall and precision much better to what we want rather than arithmetic. So this is again another issue you guys as students have to keep in mind. There is a tendency to fit the first known formula. The first known formula may not be the best formula. So you really need to look at which formula is better and why. Be able to justify your formulas and then use it rather than just picking one formula without understanding whether it is appropriate or not. So this is a common mistake that is typically done. So F1 score gives equal weight to both measures. 1 in F1 indicates equal unit weight, so that's what it is. Can be customized by using a beta instead of 1. There is also this notion of ROC curve. I'm not going to spend a lot of time on that. So this is known as the receiver operating curve from communications for historic reasons. But this is another way to evaluate your model, whether your model is good or not. So ROC curve gives an area under the curve. If you have a 45-degree line, that means it is neutral. If you have a curve that is on the other side of that, then you have more area under the curve, and then that is better than that. So that is something that you should look it up. For the example discussed earlier, compute recall precision and F1 score and compare with accuracy. So F1 score is not the same as accuracy. F1 score is considered a better way to do that. So if you look at papers, almost all papers will give you F1 score and precision and recall, not so much of the accuracy. Accuracy is okay when you are dealing with something like Jaccard coefficient, where the accuracy is very clear, either 0 or 1 or the range between 0 and 1. So Jaccard coefficient, and you can also use NMI, refined NMI and all those things, but for this one, this is a better way of doing it. And the general formula is as follows. So where instead of 1 you are using beta, so combined measure that assesses precision recall trade-off is F measure, weighted harmonic mean. If you substitute beta equal to 1, you get the previous formula. People usually use balanced F1 measure with beta equal to 1 or alpha equal to F. Harmonic mean is a conservative average C. So this is, so if you, so again we come back to this slide where sort of we are, so we did this, we are here. So to summarize, technology, computation speed, fast, cheap and large storage has moved many of these approaches into mainstream age. So, companies today can mine their complete data. Earlier they were mining 3 months of data, now they can mine 3 years worth of data. Soon they want to do mine 10 years worth of data. So the intuition or the understanding is, if you have large amounts of real data, that is better than samples. Samples will be a representative sample but not actual data. So most of the mining is today being done, like I said, on market basket data, where you're using terabytes of data to do that. And then you want to look for patterns. Can now be applied on actual data set instead of samples. Clickstream analysis. So when you buy something on Amazon or when you go to Netflix, you see a lot of stuff, right? You see, okay, oh, if you like this, you may also like these things. Where does it come from? That comes from what we call clickstream analysis. So every click you make in every purchase is stored. And then from that they compute. So this is a good example of real-time data mining, right? If Amazon shows you that information 15 minutes after you buy, you don't care. It's useless. It has to be shown immediately when you are buying something, so that you are tempted to buy other things. So clickstream analysis is being done. So imagine Amazon is using millions, I have millions of users, billions of items are bought and sold, and then they do the clickstream analysis on that for every user. So it's a personalized target marketing. It is not a general target marketing, it is for you. Same is true for recommendation systems. When you go to Netflix, it recommends you movies based upon your profile and what others who have similar profile have seen. It is not a general purpose profile. Again, this has to be done in real time. It cannot be done as a post-mortem analysis. So how do they do that? So what they do is they use the data to compute and keep lot of information which is matched at runtime in real time. It is not that they do entire data mining in real time. It is still not possible to do that. So they cull out lot of information, like they group people who have similar interests, who have similar things, and then the lookup that they do in real time is much smaller than the amount of information they have already derived from the large amount of information they have. So that's very important. We will also address data filtering aggregation in stream data. We will not be doing stream data analysis. So this brings us to the end of lecture 3. So we need to load lecture 4.